Modern computational architecture operates on a dangerous assumption. If a system successfully generates a valid sequence of code or text, it should immediately execute that action. Governed transition geometry rejects this premise. We see the core axiom here. Generation produces a mere proposal, a capability. Capability does not equal legitimacy. To prevent systems from treating their own outputs as final, we have to build a strict semantic firewall. This barrier isolates a calculated possibility from an actual committed state mutation. Without this firewall, machines execute high-consequence actions entirely because they possess the ungoverned capability to do so, interpreting raw output as permission. Preventing runaway automation requires a structural mechanism that forces a generated possibility to mathematically earn its reality before it can act. To understand how a computational action becomes real, we look to particle physics. In the Higgs mechanism, a particle has no intrinsic physical mass until it interacts with a background resistance field. A generated computational proposal behaves the exact same way. It lacks operational mass until it interacts with a system's field of constraints, memory, and authority. This equation defines transition mass, m of b, measuring the burden a proposal carries. The commit threshold, theta sub commit, marks the allowable limit. Exceeding it drops the realization gap below zero. This mathematically blocks the transition, forcing it into a repair or reject state. Reality in a governed system is a measurable, accounting-based achievement, completely distinct from the act of generation. The journey from signal to reality begins at layer 1, type-state dynamics. Every object in the system must possess a verifiable step-by-step history of its status. This diagram tracks an object's trajectory along an evidence-supported axis. It moves to stronger type states only with valid evidence, preventing type state laundering. Geometric boundaries repel attempts to bypass the hierarchy through repetition, because restating an object never promotes its status. If evidence supporting an object expires or faces contradiction, the system immediately demotes its type state to prevent false confidence. Without tracking this exact trajectory, an automated system could trick itself into executing catastrophic actions based on algorithmic rumors disguised as verified facts. Once shaped, a candidate reaches layer 3, the admissibility region. This layer asks a single, isolated question: may this candidate continue? To enter the admissible region, candidates must pierce the constraint boundary. Inside, they navigate a risk field measuring uncertainty. Survival depends on a corrigibility radius, the capacity to repair or roll back. Irreversible actions have zero radius and are violently repelled. Admitting a candidate at this stage merely permits further evaluation. It does not authorize the action to take place. Layer 3 ensures a system never spends processing power or governance capital on a candidate that fundamentally lacks safe continuation margins. Surviving admissibility grants access to Layer 6, the inner authorization region. This space lies strictly within the already verified bounds of the system. Entry depends on a rigid axiom: available governance must exceed required governance. The required governance spikes if the candidate carries critical consequences or uncertainty. When required governance outweighs local authority, the scale fails, routing the candidate to an escalation surface. Authorization is highly volatile. The permission must be active at the exact moment of execution. Any paused, revoked, or stale authority instantly nullifies the candidate. Layer 6 guarantees that mathematically viable and verified possibilities remain completely subordinate to human and defined policy authority. The strict resistance encountered at the admissibility and authorization boundaries serves a specific purpose. It assigns the candidate its operational mass. This equation calculates total transition mass. The system combines constraint pressure with compute burden and downstream memory consequences to output the proposal's massive weight. If this heavy candidate exceeds the final commit threshold, the realization gap forces a repair loop. A properly scoped candidate, one with sufficient governance and a positive mass gap, earns the right to cross the Layer 7 boundary into actualized realization. The commit threshold proves that generating an idea is computationally cheap, but realizing it is mathematically expensive. This isolates unchecked capabilities from altering system state. Crossing the final commit boundary doesn't just mutate the current state, it instantly activates the system's deep historical architecture, setting the permanent record into motion. This diagram maps the provenance backflow. Every committed action emits a layer 8 cryptographic receipt, which pools downward into the layer 9 memory basin. Following the sweeping arrows, these receipts loop back through layer 10 adaptive learning, shaping the system's future behavioral rules. This enforces the system's core topological law. The future possibility space is governed exclusively by rigorously verified historical actions, never by raw generated outputs. This closed learning loop guarantees that a learning system can adapt safely without slowly corrupting its own axiomatic rule sets over time. Equating generation with action allows ungoverned capability to alter system state without the protection of audit or constraint. Governed transition geometry acts as the computational equivalent of the Higgs field, establishing strict resistance that enforces a definitive realization gap. A possibility must justify its continuation through stability, accountability, and a clear awareness of its own consequences. System safety depends on absolute geometric firewalls, structural boundaries that force every raw capability to truly earn its right to reality.